8.3 today, we're going to be dealing with what's called key features. So imagine that this graph in front of you was a roller coaster. It's a little bit of a, it's not going to be a very smooth ride, but when we talk about key features, we always travel from the left to the right. You're back. And when we talk about key features, we are focused on the x-axis. So imagine you're in this roller coaster car and you're traveling in this direction. And we want to know when, so the x-axis is going to be time. Well, I guess not necessarily, but anyway. We want to know when is the roller coaster going up the hill, when is it going straight, and when is it going down a hill. And we're talking about x-axis, not y-axis. We don't want to know, we're not interested right now in how high it goes. We just want to know when. So if we look at this, from -5 to -3, it's going up. So this section right here is up. Also, this section, which is from 3 to 4, is also going up. And then in this section, it's going down. And then in this section, it is constant. So over here from A to B, this graph is increasing. From B to C, the graph is constant. From C to D, decreasing, and from D to E is increasing. Okay. LaShonda is riding a cable car to a lodge. Her distance from the lodge is recorded from the start of the start of the ride to the end. Let y be the distance and x be the amount of time spent. The equation -4x plus 400 models y as a function of x. And here is our graph. So use the graph to complete each part. LaShonda is blank meters from the lodge at the start of the ride. So this is time 0. So she is 400 meters from the lodge. And at the end of the ride, she is 0 meters from the lodge. So each value in the range, the y values, is a distance from the lodge. LaShonda starts the ride when the amount of time is 0 seconds. And she continues riding until the amount of time is 100 seconds. And each value in the domain is an amount of time since the ride has started. Okay, easy enough? Okay. So we want to know, determine the intervals on which the function is strictly increasing. So this piece and this piece would be increasing. And it wants to know, when is that happening? When in this story are we going up the hill? Well, that would be from -5 to -4. And we're going to use interval notation, so -5, -4. Now this is a little bit tricky. At -5, is the roller coaster pointed up the hill? Yes. So if I stick the roller coaster car at -5, is it going up the hill? Yes. So -5 is a bracket. It's an equal to. What about at -4? Is the roller coaster car facing up the hill right there? It's kind of hard to tell. On the one hand, it could be going up the hill, but on the other hand, it could be flat. And if we can't tell which is which, then we just don't pick either. So can we say that this one is equal to -4? No. So we're just going to put a parentheses. Okay? And then it's going up the hill from x equals 0 until x equals 4. When the roller coaster car is right there, is it facing up the hill? No. It's sort of between down the hill and up the hill. So 0. And then here, is it going up the hill? Well, that would be y equals 4, or x equals 4. And it's simultaneously up and down or flat. So those are the intervals. If I asked you, when is the roller coaster on a constant slope? That would be this chunk right here, from -4 to -2. Is it flat at -4? No. It's sort of between up the hill and flat. So we would say parentheses. And here, that would be -2, and it's also a parentheses. What about downhill? Well, this would be a downhill chunk, and this would be a downhill chunk. So from -2 to 0. Are we going downhill at -2? No, we're between flat and down, so that gets a parentheses. Are we going downhill at 0? No, it's between down and up. Okay, and then over here, from 4 to 7, are we going downhill at 4? No, we're between downhill and uphill. But what about at 7? Are we facing downhill at 7? Yes, and it looks like the ride stops there. So that gets a bracket. Okay, so if you can't tell if it's up or down, or constant or down, we just say it's neither. But if it's obviously up or down, then you're going to use a bracket. All right. So, I don't like this graph. Let's do a different one. Okay, this one's better. So if you were to look at this graph, and I asked you, what is the maximum value of this graph? What is the highest possible number that y can be? What's the answer? It would be infinity, right? This left side is going up to infinity. So the maximum value of this graph is infinity. Okay? What about the minimum value? How low does this graph go? Negative infinity. But there are places where you have points that are higher than any points that are nearby. So I'm talking about those two places and these two places. And in polynomials, those places are very, very important. When you get to calculus, those peaks and troughs are extremely important. And while they're not maximums and minimums, they sort of are maximums for any point that is nearby. And because of that, we call these local maximums and local minimums. And that just lets you know it's not necessarily the highest point in the entire graph, but in this region, it's the highest point. Okay? So, what are the local maximums? So when we deal with maximums and minimums, we're talking y values. So the local maximum there is 3. The local maximum here is -1. Okay? And it says, what are the values at which f has a local maximum? So this question is asking, what is the max? So this wants y values. What is the highest point in this general area? The answer is 3. What is the highest point in this general area? That is -1. Okay. This says, what values create local maximums? So this wants to know, when do the local maximums occur? That is an x value. So -2 and +1. So the first question is asking, what are the local maximums? And then the second question is asking, which x values create local maximums? And that's it for today. Today's pretty easy. Get to work.